Assalamu alaikum. Welcome to our channel. Our today's topic is magnetically coupled circuit, and we will see the dot convention as well. So what is a magnetically coupled circuit? Let's take an example. Let's take a iron core, and there will be a coil of conducting wires on it like this. Okay. I am flowing current which is going in from the left side of the coil and is flowing like this and going out from the right side of the coil. So what will happen? We know a flux will be generated there, but the direction of the flux, how will we determine it? According to a right hand rule. What is the right hand rule? We can see there is the right hand rule. If you grip the coil, the thumb grip the coil according to the direction of the current, and the thumb will break to the north pole. So flux will go out from the north pole and go in from the south pole. Okay, like this, and go in from the south pole. So flux will go out from the north pole, or if we grab this coil like the diagram, our flux direction will be rightwards. Okay, this will be our north pole, and this. Okay, now let's take another coil beside the first coil. Okay, like this. And what will happen now? We have two laws for the explanation. Two laws. The first one is Faraday's law. We have studied it previously. Faraday's law. What it says, there will be induced EMF there, and the induced EMF will be proportional to the rate of the change of the flux. So due to the flux, there will be an induced EMF, and the value of the induced EMF will be proportional to the rate of the change of the flux. But there is another law, that is Lenz's law, which says the induced EMF will be directly opposite to the rate of the change of the flux. That means if the rate is increasing, rate of the change of the flux is increasing, it will the induced EMF will decrease. Or if the rate of the change of the flux is decreasing, the induced EMF will increase. Why so? Because Lenz's law says that it will try to oppose the cause of its creation. That means the flux which was generated by the first coil will be opposed by the flux generated by the second coil. So there will be E induced, and E induced, what will it do? It will create a flux such that it opposes the flux of the first coil. So what will be the direction of the new flux generated by the second coil? It will be directed in the leftwards like this. Okay. Okay. So what we have seen here, if we flow a current in the first coil, due to the flux, a induced EMF will be generated in the second coil, and it will act such that it opposes the flux of the first coil. So it will it will create a flux in the opposite direction. Okay, so this was the example of the magnetically coupled circuit, because there were two circuits and which is magnetically linking each other. So this is basically the magnetically coupled circuit. But here we can see first coil is generating a flux, and the second coil is also generating a flux, but both are trying to canceling each other. Okay, so both are they are trying to cancel, they are trying to each other. Take another example where there is a coil like this and another coil like this. And I am flowing a current like the previous case. A current will go like this here and here. Okay, so let's see what will happen in this circuit. Let me tell you something. This is a circuit where I am flowing the current in both the coils. The current is not inducing, creating a flux, and which is inducing a current or EMF in the second coil. I am flowing the same current in both the coils. Okay, what will happen? The flux will be generated like the previous case. It will be directed rightwards. In the second coil, if we apply the right hand rule, the flux will be generated rightwards as well. So we can see both the flux are adding each other. They are adding each other. So in the first circuit, the flux was cancelling each other, and in the second circuit, they are adding each other. So therefore, the first circuit is called negatively coupled circuit, and the second circuit is called coupled positively coupled circuit. So we have a very famous device which uses the magnetically coupled circuit theory, that is the transformer. So what happens, there is a coil like this and another coil like this. Okay, so if we flow current in the primary side, like it is going in from the upper side, what will happen? A flux will be generated there. This is the direction of the flux phi. So if the flux is generated, then a induced EMF will be there in the second coil. So what will happen? Like it will try to oppose the flux of the first coil. Like, so what will be the direction of the flux? It will try to oppose. So in the opposite direction. So if the opposite direction flux is generated, then what will be the direction of the current? The direction of the current will be like this. Okay, sorry, it is going in and going out. So what is the direction of the voltage? Voltage will be the positive terminal in the lower side and the negative terminal on the upper side. Okay, so you can see the voltage are in the opposite polarity there, because I have positive here and negative there. I1 and this is the I2. The positive in the upper side and negative in the lower side for the primary side, and the positive in the lower side and negative in the upper side for the secondary side. So you can see the direction of the currents here in the upper side, the direction of the current is going in or the rightwards, and in the secondary side it is opposite. Okay, so we can see that it is basically like our first circuit. So it is a negatively coupled circuit. So our transformer is a negatively coupled circuit. Transformer is a negatively coupled circuit. Now let's go to the dot convention. What is a dot convention? See, here the current is going in and going out in the right side. Current, I haven't drawn the direction of the current. So what is the direction of the current here? You can see from with the right hand rule, if it is going leftwards, then what is the direction of the current? This will be the direction of the thumb, and if we grab it, then the direction of the current will be upwards. It is going out and this is going in. Okay, so there you can see the current is going in from the from the first coil, going in from the first coil's left side and going in from the second coil's right side. So they are opposite in direction. Okay, so let's see about the dot convention. So if you can put the dots in anywhere in the circuit, like in any terminal, any two terminal, like you can put dot in the first terminal of the first circuit and first terminal of the second circuit, or in the first terminal of the first circuit and second terminal of the second circuit anywhere. But what does it mean? It actually means if the dots, let's say I am putting dots in the first terminal of both the circuits. I have put in dots in first terminal of the both the circuits, and the direction of the dotted terminals, the direction of the currents in the dotted terminals are opposite. So it means it's a negatively coupled circuit. Okay, let's see here. I am putting two dots there in the positive in the left side of the both the coils, and in both the left sides the current is going in. So that means this is a positively coupled circuit because the direction of the current in the dotted terminal are same. So this is basically the significance of the dot convention. But we can also determine the voltage polarity or voltage, what you can say, if they are in same pole or opposite pole, we can also find it there. Let's see an example. It is dot convention is basically mostly used in the transformer. So see, I have a transformer and I am putting dot there, and this is our voltage V1, this is our V2, this is plus and this is minus. Okay, so if both the dots in the positive side, okay, or the upper side, so it means if both the dots in the same side, it means the voltages are in the same polarity. Okay, so we can determine it through the current, because if the current are in the same polarity, sorry, if the dots are in the same side but the current are in the opposite side for the transformer, we have proved that transformer is a negatively coupled circuit. So for this, if the current is going in, and for the secondary side current will go out like this. The current is going in for the primary side and it will go out for the secondary side because it is a negatively coupled circuit, so the direction will be opposite. Okay, so now we can check the voltage polarity according to the current. As it is acting as a load for the primary side, current is going in, so this terminal will be positive, and for the secondary side it will act as a source, so when the current is going out, the terminal will be positive. Okay, so you can see when the dots are in the same side, the polarity are same. Okay, the polarity of the voltage are same. If the dots are in the opposite side, what will happen? Like this. If the dots are in the opposite side, what will happen? Like here and here. This is V1, this is V2. We can see V1 by V2 for this circuit. V1 by V2 equals to N1 by N2. So that means there is no negative there, so the polarity of V1 and V2 are same. For this circuit, for the second circuit, the V1, the dots are in the opposite side. Okay, so let's say current is going in there, I1. So what will happen if the current is going in? Because of the negatively coupled circuit, current will go out. Current will go out or in the opposite direction of the with respect to the first circuit, first side or the primary side. So current is going in the primary side, current is go out from the secondary side. Okay, sorry, I have done the wrong thing. If the current is going in the primary side, current will go out from the secondary side. So direction of I will be this. This is I1 and this is I2. So this is positive and negative. So what will be the direction of V2 or the voltage polarity of V2? See, current is going out, so this will be positive and this will be negative. See, for V2, the polarity is opposite that of V1. So we can see if the dots are in the opposite polarity, the voltage will be in the opposite polarity. If the dots are in the same side, the voltage polarity will be the same. Okay, And for the currents, if we basically dot convention is used in the transformers. For the transformer, we know it's a negatively coupled circuit. So if the current is go in, then from the first side, the second side current will go out. It's pretty simple. There are the four combinations of dot convention. So let's clarify it a little bit. So here we can see in all the four cases, the V1 and V2 we have taken initially, ideally the polarity is same. According to our dot convention, we will derive the equation or write the equation. Okay. So for the first case, the dot polarity is same. So V1 by V2 equals to N1 by N2. The polarity is same. For the current, let's see here, according to this direction, according to this diagram, for the first side, primary side, current is going in, but we know then the current will go out like this. But here the I2, the current is going in for the secondary side. So I know the direction of the current will be opposite in practical. So what will be it? I1 by I2 equals to minus N2 by N1. This is basically the trans ratio, but the minus, it means the direction of I2 will be opposite. We have previously proved it, right? For the second case, the dots are in the upper side. So V1 by V2 will be equal to N1 by N2 because the polarity will be same. For the current, here, the current is going in, then the current will be go out for the secondary side. So the current is going out for the secondary side. So there will be, therefore, the current will be in the same direction. It's true. Now for case C, the current is C for the voltage first. The V1 by V, the dots are in the opposite side. Okay, if the dots are in the opposite side, the polarity will be reversed. For V2, it is plus and this is minus. Okay, so if this is plus, current is going in, it will go out. Current is going in the primary side, current will go out in the secondary side. Or you can draw it according to V2. If this is the plus, from the plus, current will go out. So this is the direction of I, and this is actually matching the direction of I2 here. So polarity of current will be the same, but polarity of the voltage will be different, because ideally we have taken the positive side of V2 is in the upper side, but actually it is in the lower side. Okay. In the last case, the dots are in the opposite side, so the polarity of voltages are in the opposite polarity. For the current is going in and current is go out, but they have taken the direction of the current is opposite side, so the direction of the current will be negative. Here you can see. So this is basically the dot convention. If you have messed up, I will clarify a little bit. If the dots are in the same side, see, for the thumb, let's take a thumb rule. So the thumb rule is, for the voltage, dot 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 on same side, voltage voltage polarity is same. Dot on opposite side and vice versa, right? So dot on opposite side, voltage polarity is reversed, or voltage polarity reversed. Okay. For the current, I am writing here for current. If for the primary side, current is going in like here, if the current is going in, it will go out in the secondary side. Primary side current going in will go out in secondary. Okay, so this was that's all about the dot convention and the magnetically coupled circuit. Inshallah, see you in the next video. Allah Hafiz.